Hello maths fans, Dr Tom Crawford here at the University of Oxford, bringing you another video in the Oxford Calculus series. Today we are going to look at what are called homogeneous first order differential equations. Now some of you may have heard of the term homogeneous before, but rather confusingly it means something entirely different here to what you are likely thinking of. In this context, a homogeneous first order differential equation is something that has the form dy by dx, since it's first order, is equal to a function of y divided by x. So any equation that can be written in this form we call homogeneous. Whenever you have an equation of this form, you use the same substitution in order to solve it. And the substitution we want is to say y, which is a function of x, is equal to x multiplied by v, where v is another function of x. So in order to substitute this in, we need to figure out dy by dx, and this will require the product rule. So if we differentiate first of all the x, so we're left with v, and then we get plus, leave the x alone, and differentiate the v term. So we substitute this in to our homogeneous expression, and what we're going to get will be v plus x times dv by dx, and that's going to be equal to f of y over x. Y divided by x is just v. So this is equal to f of v. So we can tidy this up a little bit and say that x dv by dx is going to be equal to f of v minus v. And now we can use our separation of variables technique, which I've discussed in an earlier video, to try and get the solution. So remember, we take all of the v terms across, so this becomes the integral of 1 over f of v minus v dv, and then we multiply up by the dx, treating this like a fraction, and divide through by the x. So that's the integral of 1 over x dx. So starting from an equation of this form, a first order homogeneous differential equation, we make the substitution y equals x times v. This bit is always the same, and we get down to this stage at the bottom where we've separated variables. And just as with the separation of variables technique, hopefully we can now integrate this function with respect to v, integrate this, which we can do, with respect to x, and then we substitute back and again try to get y in terms of x, which is the solution to our original differential equation. Here's an example to show you how the technique works in practice. Let's try to solve dy by dx is equal to 6y minus 2x divided by 3x plus y. So you can also think of this function perhaps as a rational function. You have some variables in x and y on the top and on the bottom. So the first step is going to be to make sure this is in homogeneous form. So remember, we need a function of y divided by x. And we do this here by dividing the top and the bottom both by x. And because it's a fraction and we do the same to the numerator and the denominator, the value of course doesn't change. So if we do that, we're going to get 6 times y over x minus 2 on the top, divided by 3 plus y over x. Now we can make our substitution where we say y is equal to x times v of x. We know that dy by dx, as we've seen, will always be equal to v plus x dv by dx. And so substituting all of this in, our equation here is going to become, let's write this as v plus x dv by dx is equal to 6 times v minus 2 on the top, and on the bottom we've got 3 plus v. Now we subtract v from both sides, so this one disappears, this becomes minus v, and of course we want this over a common denominator, which means multiplying v by both 3 plus v on the top and 3 plus v on the bottom. And then we can simplify that to now get 6v minus 2 minus 3v minus v squared, all divided by 3 plus v. And then we know that x dv by dx is equal to this. Now, of course, we can simplify the 6v minus 3v, gives me a total of plus 3v. And then we're going to take all of these terms across, so I'll just do this in one step. So we're going to divide across here to separate our variables, get all the v terms on the left-hand side. So what we're going to be left with is the integral of 3 plus v on the top. The bottom, I've got 6v minus 3v, so that's 3v, minus 2 minus v squared, dv. And then over here, as we saw before, this is just going to be the integral of 1 over x dx. And we can do that immediately and get log of x plus our integration constant, c. And of course, this will always be the same using this method. This now is the tricky bit, and this is what we have to solve. In order to integrate this function, 3 plus v divided by 3v minus 2 minus v squared, we're actually going to need to use a technique called partial fractions. Now, I will go through all of the steps in just a moment, but first we can check what we should get using the Maple Calculator app that I have here on my phone. So if I open the app and select the camera feature, I can take a photograph of this expression, and then it will load into the app, and I can now click to integrate with respect to v, which is exactly what we want to do with our function. And it says here that the answer should be 4 log v minus 1 minus 5 natural log of v minus 2 plus an integration constant. But of course, I already have my integration constant here. So this is what we expect the answer to be when integrating this expression. But I am now going to show you the steps, and we can check and make sure that we've got it right when hopefully we get the same answer. As I've just mentioned, the method we use to integrate this function involves partial fractions. So the idea is to split this up into two fractions where we can integrate both parts. Now, the first step is to actually factorize our denominator. So what we have is the numerator is 3 plus v, and then on the bottom, so I think here we're going to get a v minus 1 multiplied by, I think it's going to be a 2 minus v. So if I just double check, if I multiply this out, I get 2v, and then I'm going to get minus v squared minus 2 plus another v gives me 3v. So if you expand out the denominator here, you will get the same denominator that we have up here. And then using our method of partial fractions, we say this must be a over the first factor plus b over the second factor. But then, of course, we can now put these over one fraction. So this is actually equal to a times 2 minus v plus b times v minus 1, all divided by the product. And then the trick to using partial fractions is to say 3 plus v has to equal whatever's happening over here. So if we look at the v terms, we've got here order v. The left-hand side gives us a 1. And then the terms involving v over this side we've got a minus AV, so that's minus A, and then we've got a plus B. So that's our first simultaneous equation. And then if we look at the order 1, or the constant terms, this side tells us 3 must be equal to, we've now got 2A minus B. This is now a series of simultaneous equations. We have 2 equations and 2 unknowns, A and B. So we can solve this. So the top one says that B is equal to A plus 1. Plugging that into the bottom, we get 3 must be 2A minus 1. So therefore A is 4. That bottom equation, plugging that in the top, tells me that B is equal to 5. So our partial fractions are going to be 4 over V minus 1 plus 5 over 2 minus V. So now we're going to take this expression and plug it back into our integral, and hopefully we can directly integrate these two functions. Substituting the partial fractions into our expression, we see that we can now integrate both of these terms directly. So both of them have come from a natural log term. So here, this has come from 4 times the natural log of V minus 1. And then our second term has actually come from minus 5 times the log of 2 minus V. There would, of course, be a plus C, but I've already got it over here. So I'm combining the two constants. And this, thankfully, looks exactly like what we found earlier on the Maple Calculator app. So it's a nice sanity check that what we've done is indeed correct. We, of course, aren't quite finished, because here we have an implicit equation involving V, but V, remember, is y divided by x. So we have to substitute back because our original equation was given in terms of y and x. So in order to do that, we're going to say log of x plus c is equal to, what I'm first going to do is take these powers up inside the log using the properties of logs. So this becomes a log of v minus 1 to the 4, and then this becomes a plus log of 2 minus v to the minus 5. That's just using the properties of logarithms. Now I can combine the two logs because I have the sum of two logs is the product. So this becomes log of v minus 1 to the 4 divided by 2 minus v to the 5, because that's a minus 5. And now I'm going to exponentiate both sides. So that means taking e to the power of this and e to the power of this. So the e here cancels with the log to give me just an x, and this is multiplied by e to the c, so let's call that some constant a, where I'll write here this is e to the power c, and then when I exponentiate this side, v minus 1 to the 4 over 2 minus v to the 5. If we now multiply up by the 2 minus v to the power 5, what we're going to get over here is ax times 2 minus v to the 5 is equal to v minus 1 to the 4. And now we use the fact that v is y over x to sub back. So this is going to become ax times 2 minus y over x to the 5 is equal to y over x minus 1 to the 4. And then we can tidy this up. We need to get rid of this x on the bottom. Now it's inside this bracket sort of to a minus 5 power. So what I actually want to do here is multiply both sides of the equation by x to the power 5. So doing that, I get ax times 2x minus y to the power 5, because taking x to the 5 inside the bracket gives me an x on each term. And then on this side, I'll keep one x outside and I'll take 4 powers of it inside to get this. Now I'm going to assume that x isn't 0 because I divided by it up here, so it certainly can't be 0. So I can cancel that term. And now I have my final solution, which is to say implicitly the solution is given by a times 2x minus y to the 5 equals y minus x to the 4. So this is an implicit expression, a relationship between y and x, and this, in the square box, satisfies our original differential equation at the top of the board, which remember is our homogeneous first order differential equation. Now that we have our solution, as usual, it's good practice to differentiate this and check that it satisfies our original differential equation. Now here, we're going to need to use implicit differentiation because we have an implicit solution, but it should still work in the same way. So the first step is going to be to differentiate the whole expression with respect to x, remembering that y is a function of x. So if I do that, the a is unchanged, the 5 comes down, and then I'm left with 2x minus y to the 4. And then the chain rule says I differentiate inside the bracket, which is going to be 2 minus dy by dx. And then on the other side, we bring the 4 down and get y minus x cubed. And again, chain rule says multiplied by dy by dx minus 1. So just doing full x derivative implicitly through this equation gives us this expression. Now we want to group together the dy by dx terms so we can get an expression for dy by dx equals something, and then try and show that that something is in fact what we have up here. So if I take this one across, but I'm going to write it on this side, so I've got a dy by dx, then from the right hand side I've got a 4 times y minus x cubed term, so that's that one. Then I'm going to take that one across, so it becomes a plus 5a times 2x minus y to the 4. So that's taking that term across to the right hand side. And that whole thing, what's left on the left hand side is going to be 5a times the 2, so 10a times 2x minus y to the 4. And then this one has come across, so this was a minus, so it's now a plus 4 y minus x cubed. So this is now an expression with the dy by dx factored out. And then, of course, we're going to divide by the square bracket on both sides to get dy by dx is equal to 10a times 2x minus y to the 4 plus 4 y minus x cubed, all divided by the square bracket, which is 4 times y minus x cubed plus 5a 2x minus y to the 4. Now this certainly does not look like this, because what we have to do now is actually go back and use this relationship to help to rewrite one of these terms. So we've really got two terms. We've got the 2x minus y term and the y minus x term. So we want to substitute out one of them using this expression and hopefully get this whole thing to simplify. Looking at the expression here at the bottom of the board, what I'm going to do is actually substitute for this term, 4 times y minus x cubed. Because I know up here that y minus x cubed is actually going to be this thing divided by y minus x. So if I divide both sides by y minus x, I have an expression. So if I substitute that in, I've now got dy by dx is equal to, so the first term is unchanged, 10a times 2x minus y to the 4, plus 4 lots of this thing, so plus 4a times 2x minus y to the 5, all divided by y minus x. And then the whole thing is divided by the 4 substitute again, so that's 4a times 2x minus y to the 5 over y minus x on the bottom, and then plus 5a times 2x minus y to the 4. Now at this point, it would be nice to multiply through by the y minus x term. So if we do that, on the top I've got 10a 2x minus y times y minus x, and then it's 2x minus y to the 4th, and then plus 4a 2x minus y to the 5, and that whole thing is now divided by the y minus x goes from that one, and it's on the second, so 4a times 2x minus y to the 5 plus y minus x times 5a times 2x minus y to the 4. Now at this stage, hopefully you can see where we're going, but don't worry if not, because it's pretty complicated. But what we've got here is we can cancel the 2x minus y to the 4th from a lot of these terms. So this term disappears, this term disappears, that becomes a 1, and that becomes a 1. So if we tidy all of that up, what we're left with now is going to be on the top we have 10a times y minus x plus 4a times 2x minus y divided by 4a times 2x minus y plus y minus x times 5a. So now you'll see that we just have linear terms in x and y, which is starting to look like what we're hoping to get. So the final step is to figure this out. On the top, so we can cancel the a, because all 4 terms have a's. So we've got 10y minus 10x plus 8x minus 4y. And then on the bottom, we've got 8x minus 4y plus 5y minus 5x. And I hope this is what we should get here. So 10y minus 4y, we've got 6y. We've got 8x minus 10 minus 2x. So far so good. We've then got 8x minus 5x, so we've got 3x. And then we've got 5y minus 4y, we've got y. So it's hard work, but what we've done is taken our solution, implicitly differentiated, rearranged to get dy by dx, and then substituted back from our expression to show that dy by dx is equal to this, which is exactly the same as the equation that we were first trying to solve. Therefore, our solution is correct. So there you have it, the technique of solving a homogeneous first-order differential equation. Now remember, this method applies whenever you have an equation of the form dy by dx equals a function of y divided by x. And the first step is always the same, which is to say I'm going to let y equal x times some function v of x. You substitute this in, you separate your variables, and as we've just seen, it can get quite complicated, but hopefully you can solve the resulting integrals and then check your solution satisfies your original differential equation. As usual with the Oxford Calculus series, I've put together some practice questions in a MapleLearn worksheet, which you can access for free by clicking on the link in the video description. Give it a go and let me know how you get on. Thank you everyone for watching. Please do remember to subscribe if you've enjoyed the video, and I'll see you all soon. Take care.